Happy birthday to Thursday. Notes 8.2, multiplying polynomials. All right. So there was actually a question on last night's homework that was like this right here, except there were like parentheses around them. And of course, parentheses implies what operation? Multiplying. So when you're multiplying expressions like this, and you have multiple variables, this is one giant term, by the way. There's not like plus another thing. It's just one factor times another factor. The way that you multiply this out is you multiply like factors together. So all the numbers get multiplied together. Negative 2 times 5 is what? Negative 10. And then all you got to do is multiply the variables together by adding their exponents, right? Phones away. When the bases are the same, we add exponents. So there's an x squared. There's no other x. But if you notice, I have a y to the fourth, and I have a y to the second. So 4 of them here, 2 of them there. That makes 4 plus 2 of them, or 6 of them, right? So you add their exponents. And then z, we got some z's. We got a z to the first and another z to the first. We add those exponents. We get 1 plus 1, which is 2. So really, it's not that difficult. It's just careful record keeping. Multiply the numbers together first, and then for the variables, you just add their exponents. Okay. What if we have to multiply two polynomials by each other? Well, if it's a 2 by 2, this is 2 terms by 2 terms, FOIL works, doesn't it? Yes. FOIL works, but FOIL doesn't always work, and we've seen where it doesn't work. So here is the process that works every time. The distributive property. Here's what I would tell you to do. Take the first term right here and distribute it to everything in the other term. So we're going to get a 2. I'm going to skip all this, right? So we're going to get a 2 plus 2x, just like that. And then we're going to take the next one and we're going to distribute it to both of them. So 3x times 1 is 3x plus, well, they do it in a different order. So then you get 3x squared, which is 3x squared, plus 3x. Okay, so we just distribute it. Let's just try it out. I think you got it. 2a minus 7b times a plus 3. We want to multiply these two together. FOIL works, but let's try to do it without foiling. Let's try and see if we can leave FOIL behind us. We'll take the first term and we'll distribute it all the way through to however many terms are in that second factor. There could be 10 terms in that second factor. We would just multiply through by 10 things. There's only 2 things, though. So what's 2a times a? 2a squared plus 2a times 3 is plus 6a, okay? We've exhausted the first term. So now we go to the second term. And we take the second term, which is negative 7a, b, sorry, and we distribute it. So what's negative 7b times a? We can call it BA, can't we? But we prefer to call it AB, alphabetical order. Good. And then negative 7 times 3 is negative 21, and then we're left with the B. So there you go. It's just the distributive property. FOIL doesn't always work. FOIL only works for a 2 by 2. But the last thing you would do here is you look for any like terms. Do we have any like terms? No, we got an a squared term, we got an a term, we got an ab term, and we got a b term. They're all different. So that's as good as it gets. What order do you want to put them in? Abracadabra, shuffle them around, whatever. What's the degree of this polynomial? Squared. Which term tells us that it's squared? The 2a squared, because it has a degree of 2. Is there another term that has the degree of 2? The negative 7ab also has a degree of 2. Yeah, we add those together. That was from yesterday. Okay, sweet, sweet. All right, here's a 2 by 3. We got a 2 by 3 term, dude. Does FOIL work here? No. Does Saran wrap work here? Maybe. I've never tried that. Not on this type of problem. Let's see if distributing works. I think it will. We'll start with the 2m, and we'll distribute it to all 3 of those other terms over there. I remember when my daughter's algebra teacher was teaching them how to do this in the very beginning, in her algebra 2 class, and I was showing her at home, which she didn't like that much. Her mom helped her most of the time. But I was drawing these little lines like I'm doing right here, and she's like, "No, Dad, don't do that. The teacher doesn't like when you do that." And I'm like, "Why not? Why? It's fun to do that, and it shows what you're doing. And she was so mad when I did that because her teacher didn't like that. I don't know who her teacher was. It was at the middle school. But anyway, I was like, I need to have a talk with that teacher. That teacher needs to have more fun, right? So you draw those lines. I'm fine with having those lines there. They show you what you're doing. 2m times m cubed is 2m to the fourth power. Yes, yes? And then we move to the next one. Plus 2 times 4 is 8. And then we get m to the third power. And then we get 2 times negative 7. That's negative 14. M to the 2th power. M to the 2th power. All right, we've exhausted the 2m. We've taken it through to all three. Now we take the negative 3 and we distribute it to all three. So here we go. Negative 3m cubed, negative 12m squared, and positive 21m. We've expanded it out completely. And now all we got to do, this was kind of like the bonus on the test too. That's how I know you've already done this. This was the bonus question. Now we just got to combine like terms. So we only have one variable, which makes it easy. When you only have one variable, it's easy to kind of keep track of things. Start with the largest degree, which is 4. So we got 2m to the 4th. There's no other 4th degree term. How about an m cubed term? We got 2m cubed terms. So what are we left with? 5m cubed. Very good. 8 minus 3 is 5m cubed. How about some m squareds? Give it up for m squareds. How many do we have when we combine them? Negative 26. Verdad. Very good. And then the last guy is just plus 21m. There is no constant term, is there? No constant term. Oh, bummer. Oh, well. There it is. That's a 4th degree polynomial. And how many terms does it have? 4. So we call it a quadrinomial, right? No, Eyelid, don't agree with me. We don't call it a quadrinomial. Unless we're trying to be funny, right? Quadrinomial. We just call it a polynomial. We have monomials, binomials, trinomials, up to 3, and then we just call them polynomials. So it's a 4th degree polynomial. All right. Let's look at an application of this. Where might this show up? A rectangular prism. What's another term for a rectangular prism? A cube, right? Or a box. So you got a rectangle, and it looks like this. It's a rectangular prism. And it has these imaginary lines, which I'm so good at drawing to make it look 3D. Ooh, right? It has a length and a width and a height. Does it matter which one we call length and width and height? Does it matter? It does? Okay, which one's the length? You want to call the bottom one the length? Okay, so we'll call this L equals 2x minus 3. What should we call the width? The long bottom. This one here? Okay, that would be the width. That's x plus 4. And of course, the height would be this one here. And we can call that x plus 1. As long as you're including all the the dimensions, it actually really doesn't matter which one you're calling length and width and height. But most people, including me, would call that L, W, and H just like y'all wanted to. But as long as you're labeling all 3 dimensions, it doesn't really matter which one. It says to find an expression for the volume of the prism. How do we find the volume of a rectangular prism? You multiply all 3 dimensions together. Very good. Length times width times height. So for us, I'm going to substitute in now. The length is 2x minus 3. The width, y'all said, is x plus 4. And the height is x plus 1. Now this turns into almost exactly like what the bonus question on the test was. We just got to expand it out. This is the factored version, which is okay. Sometimes we might prefer the factored version, but the purpose of this example is to get us to expand it out. Now, I'm going to expand it out right here in the problem. So I usually take the one with the largest numbers. So I'm going to take those two. You can multiply them in any order, remember, because multiplication is commutative and associative. So just because they're not written side by side doesn't mean you can't multiply them in any order. But those have the biggest numbers. So I'm going to multiply those two together first. And I'm going to FOIL / distribute. Now, because I'm not doing it off to the side on my workbench, I have to be careful with my notation. It has to be equivalent. So I'm going to open my parentheses with the stupid highlighter. I haven't done that in a while. 2x times x is 2x squared. And 2x times positive 4 is plus 8x. And then I move to the next one, the minus 3. Minus 3 times x is minus 3x. Minus 3 times 4 is negative 12. I'm done with that, and I have to bring down the x plus 1. He's just watching at this point. He's a bystander. You bring him down. Are there any like terms to combine? Yes, so again, I'm bringing everything down. So 8 minus 3, that's plus 5x, minus 12 times x plus 1. Now I can get those two involved. If you don't like the way this looks, if you want the x plus 1 to be in the front and the trinomial to be in the back, is it okay to interchange these factors? It absolutely is. I'm okay with the way it's written if you are, because the distributive property works. It's a template or it's an algorithm. Okay? We take the first term and we exhaust it all the way through. Let's do that. I could drop the parentheses now. So 2x squared is going to get multiplied by both of those. So I get 2x cubed plus 2x squared. We're done with that. Okay, now we move to the next one, the plus 5x. We distribute it all the way through, and we get plus 5x squared plus 5x. And then lastly, we take the minus 12 and distribute it, and we get minus 12x minus 12. So it doesn't really matter if the three-term dude is in the front or in the back. The process is the same when you distribute and multiply polynomials. All right, now the last step is just to gather up all the like terms, and we start with the cubed, and there's only one of those. So I'll underline my squared terms, and I combine those and get 7. And then I'll double underline my linear terms, which are negative 7x. And then lastly, we get minus 12. If we were to name that dude, what would we name him? Fred? Maybe. Maybe Victor. His name is V, Victor. But if we were to name it by degree and terms, it would be what? Cubic polynomial. I think that was the same answer from the test. A cubic polynomial. Cubic, the degree 3, and then more than 3 terms, so just a polynomial. All right, so what this would do now is if you knew what x was, if you had a box or a rectangular prism, and you knew what x was and you wanted to find the volume, you could just plug it into this formula right here and calculate it. And then you know how much stuff it holds. That would tell you how much stuff this box holds. What would you put in a box like this? Maybe a Christmas gift, right? For your favorite math teacher, right? Maybe you'd wrap it because you're in that, and you maybe put a big bow on it or something like that. There you go. And I'd be like, ooh, this contains 2x cubed plus 7x squared minus 7x minus 12 cubic units of stuff. You were so generous for me this year. Thank you. Right? All right. Any comments or questions on that? Stuff. I got stuff for Christmas. We got a lot of boxes in the world, don't we? Yeah. Just on like my front door every day when I get home now, it's like, oh my gosh, Jeff Bezos is going to send me a Christmas card this year. Got so many Amazon boxes on our doorstep. Because my daughter's ordering stuff and she's sending it to our house from college. My son's ordering stuff and sending it to our house. My wife is ordering stuff. I'm ordering stuff. It's all Christmas is just on the front porch. Why? They're already in boxes. We shouldn't wrap. We should just let them accumulate and have Christmas on the front porch, right? Yeah. All right. The last one here. A rectangular sheet of metal, not plastic. Read carefully. Metal, right? You might need gloves for this. It has a length of 3x minus 5 and the width of x plus 2. Max! Some dude named Max cuts out 4 corners from each of these that have an area of x squared to form a box. Max is making a box out of a sheet of metal. I don't know. Maybe it's for his project for another class. What's the surface area of the box? All right, I'm not going to try and draw the box in this little area. I'm going to come down here, and I'm going to start with a rectangular sheet of metal. So let's draw a rectangular sheet of metal. There's a rectangular sheet of metal. It has a length of 3x minus 5, so this is 3x minus 5. You can call it L if you want. It has a width of x plus 2. It's metal, so if you want, you could probably like shaded gray, right? Metal. Maybe Max already cut himself on the edge while he was handling it without gloves properly, because sheet metal can be very sharp. So maybe there's blood on the corner or little blood, or there's blood around the edges where he's handling it. You don't know. Now Max, with his parents' help and permission, of course, he cuts squares out of the corner. Okay, so with his tin snips, he's cutting this, he's cutting this, he's cutting this, and they're all the same size, and he's cutting this. Okay, and he's removing this, and removing this, removing this, removing this, and maybe he's saving those for another project, or maybe he's throwing them away, or maybe he's melting them down and making some jewelry for his girlfriend for Christmas, right? Now, how does he make a box out of what's left that looks kind of like a plus sign? Maybe that's his ornament. Maybe he's making an ornament for his math teacher, and it's a big plus sign. Hope your tree's strong enough to hold this up, teacher. It's metal. Okay? How's he going to make a box out of that? It's a good question. He's going to fold it. He's going to fold the sheet metal, which there are machines called brakes that do that. But I don't know if Max has one of those machines. He may have to just use his brute force strength muscles. If he folds it up along those dotted lines, it's going to make an open top box, isn't it? An open top box. It's going to look like this, like this. It's going to have some depth to it like this. It's going to come down. It's going to look like that. But it's going to be open, right? It'll be open. So you got, well, do I want to shade it? Yes, I do. Color, Christmas colors. And then this has to be darker because we're seeing it twice, right? Yeah. I think that's how I learned in art class. See that? It's an open top box. He's putting stuff inside there. His jewelry? Ah, so the box contains itself. That's very meta. Yeah. Inception. Whoa. What did it ask us to do? Find the surface area? Okay. Now, here's what we have to first understand. He's cutting x squared out of each side. That means that this is x and this is x. This is x and this is x. This is x. This is x. This is x and this is x. How would you find the area of each of those little squares that he cut out if each side length is x? X times x. You would multiply them, and of course, x times x is x squared. So the amount that he cuts out from each side is an unknown amount x to us. It's unknown to us. Max knows what it is, but he's not telling. Okay, so I need to find the surface area. The surface area is basically the area of what we call the net. Have you heard the word the net? This is called a net. Okay, a net is when you take a three-dimensional object like this and you cut it and fold it, make it flat. It's easier to find the surface area that way because you just want the area of these shapes. So let's see what we got here. I have the area of this rectangle, which should be the same as the area of this rectangle. Yes, yes? Those are the same dimensions. And then I have the area of this little rectangle flap, which should be the same as the area of that rectangular flap. Yes, yes? And then I have the base, which ultimately was the base of the box, which I won't mess with, but that's another rectangle. So I have 1, 2, 3, 4. I have 5 rectangles I need to find the area of. But there's pairs that are the same. So here's what I need to do. What's the area of a rectangle? It's just length times width, isn't it? You just multiply the two dimensions. So if the entire thing was 3x minus 5, what should that be if I cut an x out from each side of 3x minus 5? If the entire thing all the way across is 3x minus 5, and I took an x out of each side, what should be left? X minus 5. Very good. Because it's 3x minus x minus x. Or 3x minus 2x. You see that? If we took an x out from each side, we took out 2x. So what's 3x minus 2x? 1x. Yeah. I'll show that off to the side here. Okay? It's 3x minus 5 minus 2x. And that's going to give us x minus 5. So that's this dimension right there. That's x minus 5. All right, let's take a look at this fellow right here. That started as x plus 2. And I cut an x out from each side. So what would x plus 2 minus x give me? This whole thing is x plus 2, and I took out an x from both sides. Negative x, right? Plus 2. Negative, ooh, that's kind of gross. Way to go, Max. If I do that over here, it started as x plus 2, and I took out a 2x, one from each side. I get x minus 2x, that's negative x plus 2. So this is negative x plus 2. I think I have all the dimensions to all my rectangles now, don't I? Okay, let's do the red one first. The area should be, and I'll color code it. The red one, it's going to be, first of all, there's 2 of them, so I can just double it, right? And the dimensions, what are the dimensions of the red rectangles? It's x times x minus 5. Yes, yes? X times x minus 5. And there's 2 of them. Let's do the blue ones next. Plus, there's 2 of these guys. And what are their dimensions? X by negative x plus 2. Yucky, yucky, gross, gross. 'Tis what it is, right? And then the last rectangle that I have is the base, which is what dimensions? There's only one of them. X minus 5 by negative x plus 2. Yes, yes? Yes, yes. Everyone see that? Okay. Now I've created this wonderfully delicious looking algebraic expression on the right hand side. All I got to do is expand it out and combine like terms. So let's move this box. I don't want to interrupt the flow of the problem, so I'll just move this box down. Whoa. Gotta grab the whole box. There we go. You get down here at the bottom. All right. The first thing I'm going to do is I'm just going to get rid of the brackets. I use the brackets. Uh-oh. There we go. I use the brackets just to show that there's 2 of those for groupings. But really, it's just 2 times x minus 5. Plus, same thing over here. It's just 2x times negative x plus 2. And over here, I won't expand it out. I'll just rewrite it. So that first line there was just a little bit of housekeeping. Okay, I could get rid of the brackets. The brackets just showed there was 2 of them, so I doubled it. All right, now in the first term, all I have to do is distribute the 2x. Yes, yes? So that's 2x squared minus 10x. Piece of cake, right? Next term, plus. Ooh, plus. It's going to actually be minus, isn't it? 2x times negative x is negative 2x squared. 2x times 2 is plus 4x. And then how do I expand the last 2 binomials? FOIL, or our new plan today, which is just to distribute. Okay, so we're going to take the x and we'll distribute it all the way through. And we get, I have to erase the plus sign. I'm just a positive person, but now this is negative. That's ruining my day. Negative x squared plus 2x. There we go. And then I distribute the negative 5. Hey, look, negative 5 times negative x, positive 5x. So if you're negative twice, you become positive. That's cool. Negative 5 times 2, that's negative 10. All I went through is I distributed everything out. I expanded it out completely. I call that hitting it with a little sledgehammer. Dink! The parentheses go away, and you get all this rubble that appears at the bottom. Those are just the terms. And now we just carefully go through and combine like terms. Let's see. I've got a 2x squared, a minus 2x squared, and a minus x squared. What happens with the 2x squareds? They cancel. And I'm just left with negative x squared. Gross. And then I look for my x terms. I got a negative 10x, a 4x, a 2x, and a 5x. I got a lot of x terms. Wow. Let's see. I'm going to add them from right to left. 5x plus 2x is 7x. 7 plus 4 is 11x. And 11 minus 10? Positive x. Positive x. And then lastly, the only guy that's left is minus 10. Yeah, minus 10. Now, that is a function of x. That is a way to find the surface area of his box as a function of x. If you know what he cut from each side, you can plug it in here and find the area. You got to be careful, though. Because this is a negative in front of the x squared, there might be values of x that give you a negative area. Would that be reasonable to get a negative area? No, remember, this is a parabola that opens down. So there will be some values of x above the x-axis where you can actually get positive area. But we're not interested in any negative values of a here, or 0 for that matter. If the area ends up being 0, then he cut out exactly this half from both sides and he obliterated the box. That wasn't a difficult problem, was it? We just kind of had to be very, very deliberate. Drawing a picture was very, very helpful. Coloring it gray was even more helpful because we knew it was metal the whole time, right? Carefully labeling the sides, thinking about what we're doing, and then it was just, once we got it set up, then it was routine, right? The setup should be the fun part. That's where all the thinking is involved. You're processing the problem, you're reading it, what do I need to do? And then once you set it up, it's just like, oh, now we're just sticking it in the oven, letting it bake. You just sit there and watch it bake in the oven. Is the cake done yet? Nope, there's still 23 minutes left. How long has it been? It's been 30 seconds. Darn it, right? It's not the fun part. You're just doing what you have learned to do. Expand, collect like terms, blah, blah, blah. That's the mechanics of the problem. But the setup, where you're cracking the eggs and mixing the flour, that's the fun part. That's where memories are made, right? Ho, ho, ho. Any comments or questions on this section? We're done. We're done. We never get to learn what Max put in his box. What would you do with an open top metal box? Put your jewelry? You enunciated it so well. What did you say? Jewelry. Yeah, you said he could put his jewelry in it. He could put his jewelry in it. What else could Max put inside his metal box besides jewelry? His iPad? He could use it. That he could put it on his desk. That's his iPad holder, right? His art supplies. His tin snips that he used to cut the corners with. The scraps, he could use that as his metal scrap box. He could put the corners that he cut out that he didn't make. His trash can. Yeah, very good. Okay, we're done.